Hi all, thank you for tuning in to my channel on ozone technology. This is session 7B, which will incorporate ion exchangers, filtrations, osmosis, reverse osmosis, molecular or membrane filtration. This slide will give you the principle of the ion exchanger. As the name depicts, in a fluid such as water, any chemicals that is dissolved in the water will be distributed into its ionic form, a positive ion and the negative ion. In normal water treatment, the most common ions are sodium, calcium, magnesium, and the most common negative ions are usually chlorine, nitrite, sulfite, bicarbonate. Because of the polarity of the positive and negative ions, we are able to absorb each individual ions through a ion exchange resin. There are two types of resins. One is called a cationic resin and the other one is an anionic resin. The cationic resin will exchange the sodium ion in the water to give away hydrogen ions, whereas the anionic resins will take in all the negative ions and in return will give away the hydroxyl ions. So if you notice that the sodium and the chloride or sodium and sulfide or sodium and nitrite, etc., is taken away, and instead the hydrogen and the hydroxide ions are given back. That is water. So what you will get after you pass through the exchange resins will be water. Of course, eventually both the resins get depleted and you will have to recharge them. For sodium hydroxide, for the case of cationic resins, you use hydrochloric acid to put back the hydrogen, and for the sake of for the case of anionic resins, you have put sodium hydroxide, which will put back the hydroxide ion. The next subject we are dealing with is filtration. Filtration is actually the separation of larger particles that are suspended from the liquid that can pass through the filter paper. If the solids are heavy, they can just sink and it can be separated by decantation. If the particles are light, it may be very difficult to decant. We can use a filter paper and pass through the filter paper. There are different types of pore sizes of filter paper so that you can filter different particles, suspended particles. Extremely fine pore filters do not filter the particles quickly and require some pressure on the liquid. So you could apply some pressure and you can be able to get the liquid to pass through well. When the particle size are very small, particularly in which you have difficulty going through the filter paper, and ions such as positive ions and negative ions, or sodium chloride, for example, potassium chloride. These are solids dissolved in ions, and the ions have got a particular size. They are small enough to go through the filter paper, so we have to use a molecular sieve. The definition of molecular sieve is actually a filtration system, filtration media that has got such a small pore size that it can even stop particles, big particles of molecules from passing through the filter. The filter is generally a molecular sieve or membrane filter. Of course, as you know, the smaller the pore size, the harder for the liquid to flow, and we have to use a very high pressure to force the molecules, small molecules, to go through the membrane and retaining the larger molecules. We now come to the principle of osmosis. Osmosis is a process where the solvent, the water in this case, moves through the semi-permeable membrane to the higher concentration of solute, salt, for example, until such time the concentration of the salt between the different parts of the membranes are equal. We can also apply the principle of partial pressure where the gases are concerned, where the gas can go from one part of a membrane into the other part where the partial pressure is lower. Generally, solutes will not pass through the membrane. Gases dissolved, as I did mention, which are exerting the partial pressure, will have the same principle. A good example of the partial pressure of gases is our lungs. As you know, the hemoglobin, or the red blood cell, carries both carbon dioxide and oxygen. After oxygen has been removed, the hemoglobin with the carbon dioxide comes to the lungs and get exposed to the air from the lungs. The carbon dioxide is very high concentration, concentrated in the hemoglobin, is immediately released through the cell membrane into the lung. And once the carbon dioxide has been released, the oxygen immediately enters into the hemoglobin, because the oxygen partial pressure in the hemoglobin becomes less, and therefore the oxygen enters and goes into the hemoglobin of the cell. In the tissues, the process is reversed. The flow rate, therefore, is controlled by the differences in the partial pressures, that is PO2 and PCO2. Reverse osmosis compared with osmosis. Reverse osmosis is the opposite of osmosis in that the smaller particles, water, moves from the more concentrated solution, that is a salt solution, from one side of the membrane to the other with less or no concentration of the salt. The size of the particles that move depend upon the molecular hole size, which limits the particles. You can recall the coarse and fine filters I did mention in the previous slide. As the particles require force to pass through the pores, it is facilitated by the application of high pressure. In the case of reverse osmosis, application of several hundred pounds per square inch of the membrane must be applied. Now, I have drawn a diagram to try to explain to you clearly the difference between osmosis and the reverse osmosis. The diagram in the normal, let us assume that you are using a normal filter, and the big blue dots are particles and the small red dots are water, and the brown line is a filter paper. So as you pour the water and the sediments, only the water flows through and retains the solids. So in the case of osmosis, what happens is this: the water flows into the salt. The green arrow shows that. The water flows into the salt and equilibrates. So it becomes a salt water. In the reverse osmosis, the water flows out of the salt solution and through the membrane filter. And that shows the brown arrows, which shows the reverse osmosis. This slide is just a summary of what I have already done in the previous slides. Now, it is very important for you to understand molecular filtration and reverse osmosis or membrane filtrations, which are different terms that we use. Molecular filtration, membrane filtration, and reverse osmosis describe the same process. Please ensure that you understand. In the case of molecular filtration, you can also filter the different type of molecules or ions. In other words, water ions, hydrogen ions and hydroxide ions are very, very small compared to salts and other compounds, and therefore pass through quite easily through the molecular filter. And if you want to remove, say, sodium chloride from a salt water solution through the membrane or molecular filtration, when you apply pressure on one side, you'll find that the water, hydroxide ions and anions will pass through the membrane, but all the ions which are bigger will be retained. And that is the principle of the molecular filtration or ion exchange or desalination plant. This slide has got two diagrams. One shows the reverse osmosis plant and the other one in diagrammatic form also reverse osmosis or membrane filtration that are generally used for desalination. So you can always also call these as desalination plants. If you look the diagram on the left, you will see the desalination cell or molecular filter where the water goes in and it passes through the various membrane layer, and the water without the salt comes on one end, and the remainder of the concentrated solution comes out from the another side of the system. If you look at the diagram, you will see that as you're putting the slurry, it could be salt water, seawater, pumps at high pressure onto the membrane. You find that it passes through, the water passes through the membrane system that will then be called permeates, and what is not passed through or concentrated salt solution comes out as retentate. We must understand that in the case of desalination systems, when the water is taken out of the salt water or seawater, the water that comes out, that is retentate, will have a higher concentration of salt than the normal salt water that you apply. And this very high concentration of salt is what is put back into the sea. And one of the dangers of using the desalination plants is that the amount of salt that has to put back into the sea from the same place where you take the water in, the salt concentration increases to such a level that it could impede the growth of the marine animals in that area, because they may not be used to the very high concentration of salt for them to survive. So we have to take that into consideration when we want to install a desalination plant. There are some issues that we have to understand when we use reverse osmosis in wastewater treatment. The fine membranes or molecular sieves with molecular holes are made of organic materials. In the wastewater, there are many bacteria that can feast on the organic membrane over time and make holes from the slime buildup. So filtration is severely compromised when the holes become rampant. Therefore, it is important to ensure that we maintain the membrane regularly and to suppress the growth of bacteria that will attack the organic membrane. What they do now is frequently they pass through some antiseptic or chlorine to sterilize the membrane and stop any growth that might have started on the membrane. You'll understand that chlorine can also damage the membranes. There's another question. In the case of desalination, there is a side product of desalination of seawater is excessive amount of salt that can compromise the content of the sea surroundings and prevent fish that normally live in a certain quantity of salt in the solution, water, unable to survive when the salt content increases. It is like putting a fish from the seawater, from the fresh water into the seawater, and obviously the freshwater fish will not survive in the seawater. Just to repeat that in commercial and domestic reverse osmosis systems, there is an effective high pressure of application to filter the small particle sizes, molecular sizes such as salts, and the pressures can be up to 250 to 400 psi. It cannot be achieved in the domestic units, particularly where for a filtration size, which is a pore size of 0.002 to 0.1 microns. This filtration is called ultrafiltration. Just for your information, this picture in the slide shows the relative particle sizes. And if you want to filter any specific size, you have to use a filter paper for that particular size. Coffee, ground, beach sand, table salt, human hair, pollen, that is, the sizes are diminishing as I speak of. Then anything below the pollen size, the particles are not particularly visible. That is visible to the normal eye. The limit of visibility size is given, and the size of relative, white blood cell, smoke, red blood cell, bacteria, and finally micron. So in order to filter any one away from the others, you have to have a molecular size of whole size of only the particular item, micron or bacteria, that you want to filter off. Thank you very much for having the patience to listen to my presentation. This is the end of the session 7B. Please go to the next session 8A, for fundamentals in redox potentials, polarization, flocculations, polarity, etc. If this is your first tune-in, please visit sessions 1 and 2, which will give you the complete program details, and sessions 3 to 7A. I would appreciate if you click the like icon and the subscribe icon, as this will be able to give you when we upload the next session. Thank you and have a very good day.